All right, so I'm going to try again here this is my fourth take for this slide. So what is matter? Matter is anything that has mass and takes up space, and mass is the measure of the amount of stuff or matter, not the weight. We discussed this, and basically here is this kid and here is this kid. Whereas on the Earth, he weighs 100 pounds. On the moon, we know he would weigh less because there's less gravity on the moon, so it would only be 16.6 pounds. But the reality is the amount of stuff in him did not change, and we should have something that measures that. And what measures that is mass, and the mass units are grams or kilograms. And I know here on Earth we use those interchangeably, but the reality is mass should correct for gravity. So in this case, he would weigh about 45 kilograms, and we would have to adjust the scale basically to correct for gravity. So he was 45 kilograms on the moon as well. So the reality is mass deals with the amount of stuff in a thing, to quote a student, and weight deals with how gravity pulls on that mass. So let's talk about how we separate stuff and classify things. So the universe can be divided into matter and energy. We're not really going to talk about energy. That's more of a physics thing. However, science always intersects. So we can't help but bring up some things. And we already talked about kinetic energy with temperature, and potential energy we'll talk about heat and light energy as well. But for our purposes now, let's ignore this. Let's stick with matter. And matter can either be a pure substance or a mixture. Now, how do you tell the difference between a pure substance or a mixture? Well, a pure substance can be either the element from the periodic table or a compound. If it's an element from the periodic table, you should know that here are all the elements and the names, and you'll always be given one of these. So elements on the periodic table can be either these blue metals. All these are metals on this side. There's always a staircase on there, and let me try to draw this. It's yellow on our thing, so I'm going to try to draw it yellow. It kind of starts there, and then it goes down, and then it goes over, and it goes over, and then it goes down. That looks like a staircase, doesn't it? All right, so there's a staircase here. So as you can see, if something, see, I didn't think that was, anyway, the metalloids, we're really talking about silicon, boron, germanium, arsenic, antimony, and tellurium. Those are really the ones, I guess polonium, I don't know. But anyway, they border the staircase. The ones that border the staircase that are not metalloids are this aluminum here. That has one, and I guess, is that actinium, astatine? That's an awful name. Anyway, um, the staircase divides the metals, which are blue here, from the non-metals, which are green. And I bring your attention to hydrogen. Keep in mind that hydrogen is a non-metal. It's a gas, so it belongs over here. And sometimes hydrogen has properties that belong here with this group, and sometimes it has properties that make it belong over here with this group. This is one of those times where it should be over here, but they had to put it somewhere. So you can't keep it in both places. So hydrogen is a non-metal, even though it's on the metal side. Everything else on this side is a metal. These green ones are non-metals. And I please advise you to remember, you will always have a periodic table. You know, for example, that silver is a metal. You know that copper is a metal. So if you ever have a moment where you're like, which side is metals? I forget. Just start reading things. You'll figure it out. Oxygen is a gas. You know this. You breathe it every day. So that's not a problem. All right. So elements can be either metal, non-metalloid, or non-metal, and you should understand that now a little better. Compounds. Now, compounds, like pure substances, compounds and mixtures get confused a lot. And the main difference between a compound and a mixture is that a compound always has the same composition. Let's say composition. All right. So the same recipe or what have you. So for example, salt, NaCl. I'll try to write that. I'm not very good at this. Ooh, ooh, ooh. C's are hard. C's are a little hard. But I pulled that one off, and L. All right, so that means you have one sodium and one chlorine. That's a compound. It has two elements. So the difference between a compound and an element is an element's only going to have one of these things that you see on the periodic table, whereas a compound is going to have two. So NaCl is a compound. H2O is a compound. It's the same regardless of where you get it. A compound can be either ionic, which means it has a metal and a nonmetal. Metal, now you know. It has one of the things on this side of the periodic table and one of the things on this side of the periodic table. Or it can be covalent. And covalent happens when we have two nonmetals. So often hydrogen, often carbon, but otherwise one of these green ones. That would be a metal and a nonmetal. So that's covalent. I mean, yeah, nonmetal, nonmetal. Is that what I said? I think that's what I said. So nonmetal and nonmetal is covalent. And if it has a metal, it's ionic. And remember that compounds have to have more than one element involved. If it's just one element, then we're going to call it an element. So this is a metal plus nonmetal. All right. And then there's mixtures. So mixtures are things that vary based on where you get them. So here's an example of a mixture. This is cranberry juice. And we call that mixture homogeneous because you can't really see. There's vitamin C in there, there's sugar, there's whatever it is that makes cranberries good for you, there's water. You can't really see where one begins and one ends. So we would call that a homogeneous solution or a mixture, a homogeneous mixture. Heterogeneous is where you can see different borders or interfaces. So like sand is an example of a mixture of a bunch of different rocks. You have this black one here and these darker brown and these white and different color brown. So that's heterogeneous. They're not uniform like the homogeneous one. And in fact, if we drop some ice in our cranberry juice, now we have a heterogeneous mixture because we have the ice, you can see the borders, and you can see the cranberry juice, and they're distinct. So that's a heterogeneous mixture as well. All right, mixture or compound, law of definite proportions is another way to think about it, brought to you by Proust. He said a chemical compound contains the same elements in exactly the same proportions, regardless of the size or origin. And that's the key here. Regardless of the size, more often though, think about the origin, where it came from. So water is water. And we have those bracelets that they sell that get water from the top of the world, like Mount Everest, and from the Dead Sea or something like that. So it's from a low point and a high point, but they're both H2O. It doesn't matter. It's still H2O. And whether you have a little bit of water or a lot of water, it doesn't matter. It's still H2O. So if you think of something like Chex Mix, the size, if you just take one piece of Chex Mix, it's not really representative of all the Chex Mix. So that is not a compound, that is a mixture. Whereas if you had a bunch of it, then maybe that's more so. So the size or origin doesn't matter. It's going to be a compound if it has the same composition. And here are just some compounds that I took pictures of while I was in Greece. You can see here that when the Greeks needed a sort of greenish blue color, they got this copper carbonate, copper hydroxide, and they knew that you needed two coppers in here. Not really, but they knew that if it didn't have this exact composition, it wouldn't be that color. So if you add another copper or something to this, you're going to start seeing the color change and it won't be that green. Likewise, mercury sulfide, here's a red color. And if they needed that, they need one mercury and one sulfur, and they didn't want anything in any other variation. And here's this sort of yellow orange, which has iron and sulfate and hydroxide in it. So basically what we're doing here is the same as what we were doing in biology, where you have an animal and they say, all right, what is it? It's a butterfly. So is it a vertebrate or an invertebrate? And you'd say, it's an invertebrate, doesn't have a vertebrae. Okay, is it a mollusk or an arthropod? Is it an insect or a crustacean or arachnid? So remember how we would do this in biology? It's the same thing now we're doing it in chemistry. So for example, tomato sauce. Let's look at our list here. Tomato sauce. So tomato sauce, is it a pure substance or is it a mixture? Is it something that's either an element or a compound, or is it something that depends where you get it? Well, tomato sauce depends where you get it. It's going to be different. So that would be a mixture. Now, is it a homogeneous mixture or a heterogeneous mixture? I would hopefully show you a picture of this at this point, but most tomato sauce that I know, you can see the spices in it. So we would go with heterogeneous for tomato sauce. All right, potassium carbonate, K2CO3. We are back here. And K2CO3 has elements, not one, but multiple. So it's either a compound or a mixture. Would K2CO3 be different depending on where you get it? No, because part of the statement of K2CO3 is that it's exactly K2CO3. So it is a compound. Now you got to figure out, is it ionic or covalent? Does it have a metal or it doesn't? So we go here. You have a K. You have two of those. And then C, carbon, and oxygen, 3. Now some of you might be wondering, why is it that it's not this CO? And that's because this CO has a lowercase o, as you can see. And if we go back to our K2CO3, those are both capitalized. So that means the carbon and oxygen are new elements. Every time you capitalize, you're talking about a new one. So the carbon is capitalized, the oxygen is capitalized, this O is lowercase. And that's how we know that is therefore an ionic compound. Nitrogen is an element. It turns out that it's on the, let me see if I did this. Nope, I didn't. All right, so hold on your hats for a minute. Nitrogen is over here, number 7. And so nitrogen is in the nonmetal side. It's on that right side of the staircase. And then we have hexane, C6H14. C6H14, so here's the carbon. That's a nonmetal. H is here. That's a nonmetal. 2 nonmetals means that's a covalent compound. Gold is an element unto itself. It has a symbol AU. So that's just an element, and it's a metal. And brass, this is just one of those tricky ones we like to use. It is a mixture. It depends where you get brass or what it's needed for. It'll have a different amount of stuff in it. Copper, I think it's zinc and iron, but the percentages will vary. So that is a solid solution, is what we like to say, or a homogeneous mixture. All right, we didn't do that. I decided not. Metals have luster, are mostly ductile, means you can pull them into wire. Malleable means you can hit them with a hammer. Non-metals are basically gases or brittle solids, and they don't conduct. And here is just sort of a big synopsis of the whole thing. Metals have luster, mostly solid ductile, which means you can pull them into wire. Malleable, which means you can hit them with a hammer. Good conductors of heat and electricity. Then there's that staircase. Metals are on the left side of things. If something touches the stairs, it's a metalloid, which is semi-metallic semiconductors. And then if you're on the right of the staircase, you're a non-metal, dull gases, brittle solids. All right. So then we watched the FET. We did the FET actually, where solid, liquid, and gas were made. And we realized that solid has definite shape and definite volume, whereas liquid has definite volume, but not a definite shape, right? I had water in my water bottle. It takes the shape of the water bottle, which is a cylinder. But when I drop it on the floor, it takes the shape of the floor. But the volume is still there. So if I spill 30 milliliters on the floor, it's still 30 milliliters. The volume is the same, but the shape is not definite. And then gas, of course, has neither definite volume nor definite shape. It'll just take the shape of the space it has. So one thing about the FET, if I can escape this, then you remember, this was bad timing on my part. I should have had this up and running. Please wait. FET, states of matter. That's the one. Here we go. All right. So one thing about this that was kind of cool is that if we start with neon, and we make it a liquid, you can see here it's 26 Kelvin. And neon on the periodic table has a mass of, here of 20. I believe that says, I'm old. I'm going to say that says 20. All right. So if we switch it to argon, which is heavier, argon is here. And if you read that, it's 40. So argon weighs twice as much as neon. So therefore, we would expect it would take more energy to move those things around. And it turns out that is correct. It goes up to 86. Oxygen is 16 each. 2 of them are 32. So 32 is between 20 and 40. So we'd expect it to be less than 86, which it is, but more than neon, which is 20, which it is. It's more than neon, which weighs 20. Oxygen is weighing 32. That uses more energy. And argon weighs more than that, and that uses more energy. So going back to this, let's see if this works. So it's just like you would expect with moving a rock around, that the bigger the rock, the more energy you need to move it. So that's the same is true there. So temperature is a measure of the average kinetic energy. We typically measure temperature in Celsius in the lab, but we convert it to Kelvin because Kelvin takes into account that at 0 Kelvin, and you should have discovered this in the FET, there is no particle motion. So in fact, if I go back here to neon and I try to cool it down as a solid, you can see even as a solid, things have movement, and it's not until they get to 0 Kelvin, which takes a minute, but so long as I got your attention, I will do that. You can see that that's where particle motion ceases at 0 Kelvin. There it is. Nothing's moving anymore. It's at 0 Kelvin. So there's that, and we define absolute zero as where particle motion ceases. Kelvin is the same as Celsius, except it's off by 273. So absolute zero is defined as minus 273 degrees Celsius. That's where there's no motion. The conversion is Kelvin will equal degrees Celsius plus 273. So for example, if we had 100 degrees Celsius, 100 degrees Celsius plus 273, that would be 373 Kelvin. So I can even write that in, 373 Kelvin. That thing. So minus 23 plus 273 makes it 250 Kelvin. Sorry, that's so little, but there you go, 250 Kelvin. So minus 23 plus 273 equals 250. So there you go with that. And then the final one, if we do this, solid going to liquid, we call that melting. Liquid going to solid, we call that freezing. And those you should be familiar with from middle school. Liquid going to gas at any temperature, meaning outside during the day when it's not 100 degrees outside, it's still, if a puddle forms, it's still going to go away, and that's because of evaporation. However, if you actively heat liquid to make it a gas, we call that boiling, specifically at the boiling point, the point where the liquid becomes a gas. If we want to turn gas back to a liquid, we call that condensation, like happens on our windows because of the air conditioning and the humidity. Solid, right to gas, so don't go through liquid. That's dry ice. That is sublimation. And if you go backwards, gas right to solid, so turning carbon dioxide into a solid is deposition. All right, I am happier with that version, and I am going to stop it so that you can not listen to 18 minutes.